Hey kiddos, happy lesson number 4. I hope that you're safe and well at home and staying engaged with school. It's been awesome to see so many of you in our class meetings. As we've been engaged in virtual learning, we've been talking about how what we expect to see in terms of our understanding of waves and light isn't necessarily what we always see, and how certain things like the photoelectric effect are evidence that light can act like a particle. Okay, last class we took a look at evidence where a particle could act like a wave, right? So everything isn't always as we predict it will be when we look at what is called the quantum model. So looking down at the level of electrons and photons. Sometimes there are exceptions or some surprising results from what we see. Today, what we're going to do is take a look at the quantum model of the hydrogen atom and how it is evidence for emission and absorption spectra. So back in the day, Newton took a look through a crystal, and he looked at the light from the sun through a crystal, and he saw these distinct lines that were not evenly spaced, an evenly spaced interference pattern like we would predict if light were acting like a wave. All right, so today we're going to kind of talk about the progression of our understanding of what the atom is and what it looks like, and how that is used as evidence for emission and absorption spectra, and how we can use emission and absorption spectra to identify different atoms in the composition of a gas or of a star or something like that. Okay, this is something that you may have studied a little bit in chemistry if you took chemistry, so some of this might be quite familiar. All right, so let's take a look at one of the first models of an atom. So our friend J.J. Thomson in the early 1900s theorized that the atom is a positively charged sphere in which negatively charged particles are scattered. He called this the Plum pudding model. He's a Brit, and so plum pudding, I think it's like a cookie with a raisin or something. I like to think of it like bread pudding. If you've had bread pudding, it's just like bread soaked in custard with little raisins kind of throughout. For me, I enjoy chocolate chip cookies a lot more. So I like to think of his model like the chocolate chip cookie model, right? Where you've got a blob of dough and then semi-randomly but evenly spaced kind of chocolate chips. That was the whole idea. So all of this blob part was positive, and all of these guys were electrons that were negative. He hadn't named them electrons yet. There was just kind of the positive space and the negative space. Okay, and here's another visual for that from a simulation that I'm going to show you here in just a second. Okay, so the simulation that I'm going to show you is going to model what's called Rutherford's gold foil experiment. This is a PhET simulation, and I'll attach it to the Google Classroom. But I want to use that simulation to talk about what Rutherford expected and what actually happened. Okay, so this is called Rutherford's gold foil experiment. Quite frankly, it was mostly done by two scientists named Geiger and Marsden, and he took a source of alpha particles. An alpha particle is just a helium nucleus. Okay, and it's 2 neutrons and 2 protons, right? So its net charge is positive and has a charge of twice the elementary charge. Okay, So it's just a nucleus with a positive charge. Okay. So they took this beam of alpha particles, sent them through a slit, okay, towards a piece of gold foil. Okay. Now, if those alpha particles were interacting with a blob of positive charge that was interspersed by little negative charges, you would expect something to happen like this. So this is our blob of positive charge, little blue negative charges. And then over here, this is the gold foil. And then we're blowing up really big, what we would see. I'm going to turn on these alpha particles. There are those alpha particles. And we would expect them to just kind of fly through that region unchanged for the most part. If the positive and negative was evenly spaced, most of those alpha particles would be affected uniformly by that charge. Right, the charge would actually be fairly neutral, right? Unexpected, or the alpha particles, maybe if they came close to a particular electron, may have been attracted a little bit to it or something like that. You'd see very little deviation from the direction that they were being shot. So here are the expected results, right? Very little deviation from their original path, okay? But what they really did see is something unexpected. When they shot those alpha particles at the gold foil, they saw some of the alpha particles, right, went straight through, just a few. Some of them got deflected at an angle, and some of them bounced back. And that was the most surprising. So let's take a look at that simulation again. So this is Plum pudding model. Take a look at the Rutherford atom. Okay, so this is what really happened, where we shoot some alpha particles. Okay, and this one, the alpha particles are purple. Okay. And you see some of them going straight through, and the ones that get close to these little yellow dots are deflected significantly, and some of them come so close to those little yellow dots that they bounce backwards, right? See, whoa, that one went all the way to the side. Okay, so this is surprising, and we have to talk about what that means in terms of what the atom actually looks like. Okay, so let me find my notes. Okay. All right. So as a result of what he saw, Rutherford then theorized in 1911 that all of the positive charge of an atom is at its center, and it's condensed in a really small center. He theorized as a result that electrons whirl around it and that the atom is mostly empty space. And that's the only, especially the idea about the nucleus is a reasonable way to be thinking about it, especially if there were some electrons or alpha particles that were repelled backwards and some that were allowed through. Okay. And he said that he was so surprised by what he found here. It was as though he were to shoot an elephant gun, right? A gun with a very large bullet. Again, this was 1911. As he was so surprised as if he had shot an elephant gun at a piece of tissue paper and the bullet came bouncing back, right? That's how surprised he was by the result. Okay, if he could shoot a bullet at a piece of tissue paper and that bullet came bouncing back. All right. So there are some problems with this model, specifically the idea that electrons whirl around the positive nucleus. And that's because if you had like a nucleus, okay, let's say you've got this positive nucleus, and everything is black today, this positive nucleus, and you've got like an electron out here whirling around. Okay, so he said that an electron can be out here and it can whirl around, so we can pretend like it's in circular motion with some tangential velocity. If it's moving in a circular path, the centripetal force would be, the electric force, right? The electrostatic force. Okay. And if there's a centripetal force, that means that there must be some centripetal acceleration. Okay. But what do we know about electrons that are accelerating? We know that if electrons are accelerating, they emit light, right? And light has energy. Okay, so electrons that are accelerating emit light. And light it has energy that can be calculated using E equals hf. And so that means that if an electron is whirling around the center of a nucleus, it's emitting energy, it's losing energy. And what happens to a satellite or something in circular motion that's losing energy? Well, it will swirl, 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 and eventually crash into the nucleus. And that's what we know is not happening, because we are not constantly getting light being emitted from all atoms. And we've got evidence that atoms are fairly stable. Okay, so there's some good things about this model, right? We found evidence that the positive charge is concentrated in a small location and not spread evenly over the entire atom. But the swirling electron business is a little bit difficult. Okay. All right. So again, one main difficulty is that an accelerated charge would radiate electromagnetic waves, lose energy, and not move in circular paths. And then if electrons use energy, they would eventually fall into the nucleus. And this doesn't explain why some matter is stable, just like I said here. All right, and then a few years later, our friend Bohr came along, and this is a model that you've seen a lot. He said that electrons can move in paths a certain distance from a nucleus that are called energy levels. And this is often used as our two-dimensional representation of an atom. So here we still say electrons move, but it's a little bit more complicated than that. They're not moving, they're existing at certain energy levels, and electrons have a certain probability of being in each of those energy levels. And I'll draw you a picture here in just a second. Okay, so Bohr found that an electron could exist in a specific energy states of definite energy without radiating that energy away. Okay, so he is trying to come up with a model that didn't have the electrons orbiting, because there is some cognitive dissonance there with what we previously knew about electrons and orbital motion, right? So if electrons could be at specific energy levels, an electron's energy is discrete, right? It's what's called quantized. It's got a certain value, and that's where we get the name quantum mechanics, right? With the idea that an electron's energy is quantized.